So in the last class, okay, we were actually looking at singular value decomposition, SVD, and we were almost at the end of SVD. I just wanted to actually point out that there are certain applications of SVD, some of which you have already seen and some of which I would like to point out now. So the applications of SVD, right, as I said earlier too, okay, it has a lot of applications, right, left and right it has been applied. One that you've already seen is in homography estimation. Okay, so the homography estimation part, you've already seen that. Homography estimation. Then other than homography estimation, right, you've got to say other applications such as well, in fact you can even, it is also used to compute the eigenvectors when you do a PCA. For example, right, when I talk about PCA, right, what I really mean is if you kind of look at S as some rectangular image and you expand it as A sigma B Hermitian, where of course we realize that A is M cross M, sigma is M cross N, and B is N cross N, where A is individually unitary, B is individually unitary, and sigma is a diagonal matrix, but it is rectangular. Right. One way to kind of look at it is we do some kind of image expansion, okay, where we said that this is also equal to summation sigma I, AI, BI is Hermitian, where we said AI is the ith column of A matrix, BI is the ith column of matrix B. Okay, this is one way to kind of look at it, where I goes from 1 to R if R is the rank of S, right. So you kind of you do an expansion over all the using all the singular values. Now this is one way to see. Okay, this is what we have already seen. Okay, now let me just remove this PC and rather say image expansion. Okay, but then it is seldom used for this. Okay, it's seldom used for image expansion, but we still want to point it out because of the fact that this is an image transforms chapter, and therefore it makes sense to talk about image expansion. Now the other thing, right, when I talk about its use its linkage with actually the PCA, okay, it comes about like this. If instead of looking at this as a rectangular image, suppose you think about S as a data matrix. Suppose we can go back to that example, right, where we had to do something like a face recognition. Now each of those faces at the time that we were talking about was like 64 cross 64, which means if you stack it up as a vector, it comes out to be a dimension 4096. Now suppose you had several face images and you stacked all of them as columns here, right. So it's like saying that each so there are 4096 rows because each example, so each of these is a face. Okay, this is like face 1, this is like face 2, and so on. So suppose you had p number of such faces, right, which could span different individuals and so on, and where of course p expectedly, p surely we need this to be much larger than 4096. Okay, so that means you have a 4096 dimensional vector, but then you've got lots and lots of examples, example faces for you, and suppose you stack all this up within in this matrix S, and suppose you generate a new matrix S, suppose I call this S underscore, and suppose we make this as S minus some, let's say, mu, okay, where this mu is simply the average of all the columns in S. Okay, what that actually means is that with respect to the face example, it would mean like the average face, but in general, right, it could be anything. I mean, this could correspond to faces, this could correspond to some other kind of a data set, whatever it be. So mu is the average of all the columns in S. So if you do this, then you're doing some kind of a mean subtraction, and suppose you did S transpose, right. I'm not writing Hermitian, strictly speaking it should be SS Hermitian, or okay, if you wish, we can do it as SS Hermitian, because that is what you would do in general. Okay, if this matrix had some complex entries and so on, then that would give you a covariance R, that would give you the covariance of this, say, data. Right, so in other words, what you would have otherwise estimated as R is equal to, suppose you had P examples, you would have estimated it as 1 by P. Let's say each of these examples, suppose I call them as Xi, then what you would have done is Xi minus this mean mu into Xi minus mu Hermitian or transpose. Generally it's a transpose, but well, you can use the Hermitian. Now if you were to do, right, so For example, this is a column vector, that's a row vector, therefore you get actually a matrix. You sum up all these matrices so as to get an idea of the covariance. The same effect that you would get by doing this operation is what you get by doing this, which is simply SS Hermitian. Now, if you substitute through singular value decomposition, we know that S by itself, which is a rectangular matrix, can be kind of decomposed as A sigma B Hermitian. Then we know that this will turn out to be A sigma B Hermitian into S Hermitian is B sigma Hermitian A Hermitian, and because B Hermitian B is identity, you end up with A sigma Hermitian A Hermitian. And of course sigma Hermitian, as you can clearly see, is 4000. So this is 4096 by 4096. Okay, and R again of course is 4096 by 4096. If you take it to be the special case, then this matrix, this is a covariance and it's of size 4096 by 4096 if you do SS Hermitian, right? So what it actually means is that if you wanted to do an eigenvalue eigenvector kind of a decomposition for this covariance matrix, then those eigenvectors that you need to do this decomposition can come straight away by doing the singular value by doing an SVD on S. So you could take this data matrix, do the SVD, and by doing SVD you would get this A, which is what you need in order to write the covariance in an eigenvalue eigenvector form. And the singular values that you get in sigma can then will also need to be used here, right? So if you just plug them all here, right, your eigenvalue eigenvector, say, right, a decomposition is sort of ready. Now you can see which ones to use, which one, how many significant eigenvectors and so on. So in that sense, right, there is also, in that sense it is very closely knit to the PCA also. And then there are of course applications of like denoising, which is something that we will see later. Okay, when we do transform domain filtering, SVD can also be used for some kind of denoising, image denoising. And one more thing that I would like to point out is what is called pseudo inverse. Okay, so like I said, it has several applications. I'm just kind of mentioning a few here. I'm just listing a few of them here. Now, by pseudo inverse, right, what we really mean is this: a pseudo inverse. Okay, so it basically means that right. Generally, you would think that you would kind of talk about inverses of square matrices, right, provided it exists. Now, when you talk about pseudo inverse, you can even talk about inverse of a matrix which is just rectangular, and so on. So what this means is, so it's not really, so in that sense, it's kind of a weak inverse. It's not the true inverse, right, that we've all learned. It's called a pseudo inverse. It's also called the Moore-Penrose pseudo inverse. Moore-Penrose pseudo inverse. And what it means is this: suppose I have a matrix SMN. Okay, let's say that I have done an expansion as A sigma B Hermitian. Okay. Now, of course, again this is M cross M, M cross N, N cross N, and the pseudo inverse is is typically indicated by actually a plus on the top. And this will have a dimension N cross M. Okay, and that is given as B. Okay, and sigma plus, which will then become N cross M, and A is a Hermitian, where sigma plus. So if sigma, let us say that suppose S was 2 cross 3, suppose as an example, then the sigma, right, would this matrix sigma, which is actually 2 cross 3, right, would then look like this: sigma 1 0 0 0 sigma 2 0, right? Then the sigma plus would then look like, so the sigma plus will of course be 1 by it's N cross M, right? Therefore 1 by sigma 1 0, then 0 1 by sigma 2 0 0. Okay, because sigma plus should have a dimension N cross M, which will be 3 cross 2 now. Okay, so your sigma plus, which is now 3 cross 2, right, would look like this. So in general, okay, so sigma plus will simply mean that whatever singular values which are right non-zero, you will just take their reciprocal. So you will make it as 1 by sigma I. Okay, and which is what would then kind of lead to sigma plus, and then you can use that to compute your S plus. And this S plus is called the pseudo inverse, and it satisfies, it's kind of a weak inverse. This guy will satisfy S plus S is equal to S, or S plus S plus is equal to S plus, and so on, right? So in that sense, it's kind of a weak inverse. right? But and when the actual inverse exists, suppose the actual inverse exists, then the pseudo inverse will then be equal to that. If in case the true inverse exists, okay, then in that case it will be equal to the pseudo inverse will then be equal to the true inverse itself. In other cases, you would get something like this. Okay, so this sort of ends our ends is SVD, right? So we've gone through SVD, we've gone through also the applications of SVD.